All right, we are talking about our new unit, polynomials, and this video is really going to be mostly idea-based, which is thrilling, I'm sure. So, hold on to your horses, or I don't know, to your seats. Hold on to your seats. There we go. That's what you should hold on to. You can let your horses go. For this video, it's not going to be very thrilling, I know, but we are just starting off some of the ideas that are going to lead us through math throughout 20-1 and 10C and 30, not in that order, but all the higher level maths in high school this is foundational. So kind of a big deal. Now, we've already dealt with some sorts of polynomials, which are linear functions. And they still fall under this bigger definition, which we'll talk about in a minute. But we've only really dealt with a tiny little fraction of them. And so before we kind of get into what a polynomial is, let's talk about what is a linear function. Well, you might remember a linear function from our slope-intercept form that we've talked about before. So y equals mx plus b. Yeah, so we remember that. We remember, okay, a linear function, depending on what our slope is and what our y-intercept is, it makes a line. And so maybe it's like this, or maybe it's like this, or who knows, right? It could be very steep, very shallow, positive, negative. It could start way down on our y-axis or way up on it. Lots of options. But okay, we know that, but why is it always a straight line? And the reason comes from the application of a slope onto just x. So with this creates a constant rate of change. Constant rate of change. And the reason for that is that every time m changes, or rather m doesn't change, every time x changes, m applies to it consistently, constantly. It's linear. It happens all in a very kind of scaled way. Whereas if we had something other than just x, it would apply differently. And so what makes it linear? Having just x. So another way we can say this is x has to be a first degree. And so this means that there's just one x, right? Or x to the power of 1. And that's different than if I wrote something like x squared, which has a huge difference now. If that m were attached to an x squared, it would totally change the shape of our graph. So our linears are linear because they have a degree of 1. And I'm using this term degree. That might not actually be a word in your vocabulary yet. Hold on to that thought, because we're going to talk about the definition for that term. But for now, we got this guy here, 1. If there's a 1 as its exponent, we're good. So let's talk about what polynomials are. And over here, we'll come back to this maybe, or maybe not. This is just something I did in class, so just leave that for now if you're just going through the notes. In order to understand polynomials, let's talk a little bit about algebra tiles. And we had sort of 3 kinds of algebra tiles. We have these little squares, the long rectangles that are wavy, I guess, and the big squares. Okay, so with these are something we've seen before. We notice that one side is green or a different color and one side is red. These help us represent the different sort of algebraic statements that we can use in polynomials. Oh gosh, ignore that bit. We can consider that the smallest building block here is like a value of 1. And down here, when it's red, it's -1. And think about an area model. This is 1 because one side is 1 and the other side is 1. So it's like a 1 by 1, which creates a value of 1 square. Our other one, this side here with our actual algebra tiles we see in class, is sort of a weird mix. It doesn't actually scale perfectly with our 1s. And there's a very, very particular reason for that. It's because it's supposed to not fit perfectly, because this is some sort of indeterminate quantity. We'll call it x. Well, the other side, though, the width of our x length rectangle is 1. Because it matches up perfectly with our shape here. So these shapes, this side matches up perfectly with this side. And so if we consider the area of this, we've got 1 times x, and well, anything times 1 is just itself. So the area of this x tile has an area of x. That's why it's called an x tile. And then we find, hold on, this side length is the same as both side lengths on the bigger square. And so it's x times x. Well, we know any number where it's like x times x, if it's the same number, we can write that as a exponent or power x squared. Neato. So now we've kind of got an idea of why these are labeled like this. How do we work with them? And we'll be able to use polynomial tiles or algebra tiles later on for a lot of things. For now, also don't forget we've got negatives. And with these, excuse me, we can represent a lot of different things. Okay, let's get on to some more complex and maybe drier parts of this. We've got a lot of words we need to work on, and we want to just focus on the words as they apply to the expressions and the functions. And if you can attach them to algebra tiles, great, but if not, then that's totally fine if we're more focused on just the algebra itself. So let's actually define what a polynomial is finally. And for most of these terms, I'm just going to say them out, the words that I want to say, and then I'll write some stuff down, but I don't want you to have to look at all the stuff I write down. So if you want to write it down yourself, then just listen to the video. And if you need to go back, just rewind it. There's a button for that. So first off, a polynomial. Poly means many, and nomial essentially means terms. So a polynomial is a collection of terms where we've got a collection of terms where we have all of the terms having a whole number degree. So it's a collection of terms and it's all whole number degree. So I'm gonna kind of spoil this definition a little bit, but I'll say this: 4x squared plus 3x minus 5, this entire thing is a polynomial. Okay, because it's a collection of terms, and terms is something we're going to need to describe better, and it's got a whole number degree or whole number degrees for all of its terms. And that might not make that much sense, but over here you see all these, well, 4 is a whole number, 2 is a full number, 3 is a whole number, 5 is a whole number. So all these are whole numbers. So that's helpful. Okay, let's move on to our next definition. And if you feel a little confused of what polynomial means right now, that's because we haven't finished describing it, but we're going to need all the other parts to sort of fill in the picture. A term is a single part of an expression. So it's one part of the expression. One part of the expression. Parts, of the expression. And we can describe a term as being something that's sort of attached to the rest of them by addition or subtraction. So 4x squared, 3x, and 5, or well, really we should say negative 5. These are terms. So in this polynomial, there are 3 terms. Another thing is, like, if you think about the number 12, 12 is the same as saying like 3 times 2 times 2. And so 12 is 3 times 2 times 2. So it's not like I've got, well, a 3 and a 2 and a 2. I've got just this one big idea. And so if I have things multiplying like 3 times x to get this 3x, that's still all one term. And the same for dividing. 12 we could say is like 24 divided by 2. Even though I've got these 2 sort of parts, because I can kind of combine them into the one idea, that makes it a single term. A variable, I'm not really going to write anything down, but x in this case is a variable. So a variable is a representation of an indeterminate or undefined quantity, or a quantity that can change over time. So we've dealt with variables for kind of implicitly almost 9 years, really. Like even in grade 1, you kind of say the smiley face plus 1 equals 3. What's the smiley face? Which is how grade 1 teachers sound, I guess. And so this kind of is acting like a cute little variable. Nowadays, we're just going to be using x. And so in the polynomial above, x is, of course, a variable, and that x obviously is still a variable. Coefficients are the name of a number multiplying onto a variable. So the number multiplying onto a variable. So number onto x. So in this case, 4 is a coefficient. And we should actually clarify this a little more. We should say instead of just 4 being a coefficient, we should say it's positive 4. If there's no symbol in front of it, it's kind of implicitly positive. And this is positive 3. Now we can see, oh yes, it's plus. So positive 3. These are both coefficients in our statement because 4x, well, that 4x squared means the 4 is multiplying onto a variable. And the 3x, 3 is multiplying onto a variable. Constants are numbers that have no variable attached. And in this case, -5 is the constant term for our definition above. So -5, excuse me, is our constant term. A couple other ideas. Now we can, we talked a lot about terms and what make up terms. Now we can talk about what degree means. And remember, we said a polynomial has to have whole number degrees for all of its terms. And so if this is a term, this is a term, and well, really we should include the signs above, right? Or in front. So let's do that. This is a term, this is a term. They all have to have a whole number degree. And degree is kind of a bit nifty. So make sure you get your head around this. Take the time to think about it. Listen to me say it a couple times if you need to. Degree is the sum of all exponents on the variables for any given term. And we'll do a couple examples of this in a term. So our first example is, I guess, the one above. If I look at 4x squared, I look for the variable. There's only one, it's x, and it's squared. And so the degree for that will be the sum of all the exponents. If there's only the 2, then there you go, it's 2. Now, it doesn't matter if this is 4x squared or -4x squared. I'm just looking for our exponents, and boom, that's the degree of this term. Over here, I've just got 3x. Well, that x kind of implicitly has the exponent 1, and so my degree is 1. And then for -5, well, there's no x, so there are no exponents. We can say 0. We talked about with polynomials, remember that they have to be whole numbers. So 0 is fine, 1 is fine, 2 is fine, 200,000 is fine, but you're not allowed to have like -2. This is a no-go. You can't have x to the -2, and you can't have x to the 1/3 or anything like that. That's just as bad, if not worse. So both of these are no-goes because we want to make sure that we have just whole number exponents. You can also have something like this where we've got a squared b cubed c squared. And what's the degree on this? Well, now I have more than one variable all added in together. I shouldn't say added in together, right? We see that's multiplied together. If I have this, I take the sum of all the exponents in this one term. Since it's all multiplicative, it's all part of the same term. So I've got 2 and 3 and 2. So 2 and 3 is 5, and another 2 is 7. Our degree here is 7. Now, the degree of a polynomial, so if this is the whole thing is a polynomial, is the degree of the highest term. And we can clarify that a bit by saying the degree of the highest degree term. So what that means is for our polynomial up here, the biggest number is our degree of the overall polynomial. So 4x squared plus 3x minus 5 is a degree 2 polynomial. And you might be thinking, well, hold on, what about this? What if I had like x squared versus x squared plus x? So like one of them has 3 x's written there. So shouldn't it have a different degree than the one with just the x squared? And I say, that's a good question, but no, it has the same degree. So we'll talk about why here in a second, but let's show how I got the degree of 2. For this, I'm looking at my one term. Okay, it's got a degree of 2. And so since there's only the one term, we know that that's the degree of the overall polynomial. Here we've got a degree 2 term and a degree 1 term. To find the overall degree of the polynomial, all I have to do is look to see which is the highest degree term, and well, it's 2. 2 is bigger than 1. I'm pretty good at math, I know. And so there we go. We know it's degree 2. Both of these are degree 2 polynomials. And the reason why we want to talk about degree for polynomials is that the type or the shape of a polynomial, or you could say the characteristics of a polynomial, most heavily depend on their degree. And so what I mean by this is that if I made a graph out of something, like we made lots of graphs out of linear relationships, which we now know are also polynomials. But if I graphed this, right, I made a table of values, I plotted my points and I graphed it out, then its shape would be most influenced by the fact that it's got an x squared. So that x, yeah, whatever, that'll have an effect. The -5, sure, our graph's going to move down 5, and all these coefficients matter too. But the most important part of it is that it has an x squared. So the degree of the polynomial is the most important part. If you want to go back up on the page that had all the room for graphing, why don't you try graphing a couple examples, see what sorts of things you've got. And that should show you that degree is the biggest influence. Last but not least, for definitions, binomial, trinomial, monomial, these are really helpful to know because we can do a lot of different math more easily by using these 3 terms, but we don't really go into like tetra or pentanomials or anything like that, because binomials and trinomials and monomials, with those, we've got tons and tons of tools we can work with. So binomial, you might remember the prefix bi as in like bicycle. So that means 2 terms. So an example of a binomial would be x squared plus x. Tri means 3 terms because it's a trinomial. So here's one, x cubed plus 7 plus 3x. Okay, and a monomial, like monochromatic, I love that word, I don't know why. Anyways, it just means 1. You got only 1 term. So 7x cubed y to the power 4. There's a term that is a monomial. Okay, let's I'll leave this for you if you want to just practice some stuff up. Let's should we include that? Yeah, let's include one last idea. That last idea is like terms. So when we are dealing with polynomials, one of the things we'd like to do is organize them, simplify them. Anytime we want to do math with a polynomial, we really have to get a good grasp on like, what are we actually working with? And so we are going to use this idea of like terms, which is a way we can organize them. Like terms are terms that have the same variables and same exponents. Okay, so a term like 7x is alike with a term like -4x, or a term like 3/9. Well, that's a stupid fraction, but anyways, 3/9x. Because they all have this x, and because the exponent is the same, so I shouldn't put, I was drawing a circle where the exponent is, it's not 0, it should be like 1. This is there, and that's a 1. This is there, that's a 1. Since these all have the same variables with the same exponents, they're alike. Something like this, x cubed y 4, is the same or like as -3x cubed y 4. Some things that aren't alike, like if I had 3x and 3x squared, these are not like terms because you have the 2 here versus a 1 here. So when we're looking for like terms, we aren't going to look at our coefficients. We're not going to look at if it's positive or negative. We're only going to look at the fact that it has the same variables and it has the same exponents. With those, that makes it a like term. So let's take a look at combining like terms. In general, if you're combining like terms, you essentially can just add the coefficients. So think about like if I had 3a and negative 2a, it's like I have, okay, well, I have 3 of, well, sure, we'll say the a's are like our little algebra tiles. So 1, 2, 3, and they're positive. Whereas over here, I've got negative 2a's. We remember from our work with integers last year that if I have a base pair, which is a pair of a positive and a negative, they cancel out. And so I'm left with just one a tile, which makes sense because if I think about my coefficients, if I combine them, 3a and negative 2, well, 3 minus 2 is 1. And so here we go. We've got our one tile left. Okay, so using algebra tiles, we can collect and simplify the following collections of terms. I'm not going to do that. You should practice that on your own using sort of the tile methods up here. But I'm going to show you another way. And this way is much more helpful if you do not have any terms that fit well with algebra tiles. So for example, for AB, yeah, we don't have AB algebra tiles, not really at least, so we can't make it work. Okay, let us see which of these are like terms. What I'm going to do is I'm going to look for terms that have the same exponents and variables. So with this one, oh, hold on a second. Well, they all have the coefficient 4. They've all got this a, but we've got b to the power of 1, then 2, then 3, then 4. So this is something that you might see. You might see probably not a question where all the terms are like this, but a question where a lot of, or some of the terms at least, are similar looking. And they're trying to trick you. They're trying to say, well, some of these have to be similar. There are no like terms, here. So they might try and trick you with that, but you keep your eyes open and you'll be fine. Now, if I'm going to group like terms, here's a strategy that I can do. Now I see that some of these are alike, just kind of scanning it. What I'm going to do is, using different colors or the same colors, I'm going to go through and I'm going to start with this term and I'm going to put something like a circle around it. And now I'm going to look at all my other terms, and they were nice. They put commas around to show me which ones are which. I'm going to look for anything that has an x with no exponent and a y with no exponent. So no, that's x squared, that's y squared, there's 4, so that's neither. XY, oh, this one's got a squared, so that's no good. Okay, hey, here's an XY. It's got a different coefficient, but that's totally fine. I'm going to put a circle around it as well. Then I'm going to go back to my hunt, make sure there's nothing left. No, there's none. Okay, then I'm going to start with my next term. And I'm going to put a different shape around it. I'm going to put a square. And so this term has x squared, so I'm going to look for any other x squareds. It's y, no, 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 no. Oh, okay, well, that's it. Then I'm going to go around, I'm going to change colors. So I'm going to put a red circle around y squareds. And I'm going to say, okay, is there any other y squareds here? No. Oh, well, that's got an x, so that's not going to work. 19. Oh, here we go. Another one. And sorry, that should be not a square, but a circle. And let's use a different color. Let's do the color method. Any constants, so no variables. No, that's got variables, and there's this. And this guy's kind of on its own. And once I've gone through and I've kind of made the shapes, some triangles and boxes and circles, then I can say, okay, let's collect all of the similar shapes. So for the black circles, I'm going to move all those terms over here. 4xy minus 4xy. So I've got 4xy and negative 4xy. Okay, any black boxes? Well, there's just negative 2x squared. Okay, any red circles? Well, I've got 16y squared and negative 4y squared. And then finally, our last term here is 9xy cubes. Oh no, and I missed the constants, xy squared. And then our constants were 4 and 19. Now I'm going to go ahead and I'm going to combine them. So I'm going to look and see, just like kind of thinking about our algebra tiles and how base pairs cancel out, or how we can use just our coefficients, combine them as integers. I'm going to just put these together. And anytime it's positive, I can think about like adding. And anytime it's negative, it's like subtracting. So if I had positive 4xy and negative 4xy, these guys will cancel out and leave me 0. That's depressing. This doesn't have anything to pair with, which is arguably even more depressing. So it just stays like that. Over here, we have 16 and negative 4. So that's like 16 minus 4. So we end up with 12y squared. This also doesn't have anything to add with, so we'll just write it as is. And then we've got a 4 and a 19. They're both positive. So it's like 4 plus 19, which is 23. Interesting. So now we've got all our different ideas. What we can do is we can write them all down. And we like to order things in terms of highest to lowest degree. So I'm going to start with the one with the most degree. This is 0, so it doesn't have any degree. This is a degree 2. This is a degree 2. This is a degree, well, there's a 1. So 1 plus 2 is 3. And this is also degree 0. So I'm going to start with this term. We'll go 9xy squared. Then this term, minus 2x squared. And notice how, as I write this, oh, hey, like if I just put that this is negative, it already kind of makes a polynomial. For this one, I just have to put it's positive. And then plus 23. Not 32, 23. And that gives me a collection of like terms into a polynomial. Okay, that's all for this video. Hopefully you guys find it helpful, and I'll see you in the next one.